And it's but we're left and before I sort of recap where we were last time, are there any questions? Also means on something like this. You want it to be like left side down. Potentially, I can share with you the text over here. Probably anything easy way to do that. It's somehow in the template, but that sounds. Under the proof well, yeah, there's quantile for your like. Sure. Send me an email. I can give you access to like the overview in which this exists, so that it gives it some format. There's some simple way of doing it. Regular thing. Good. Other questions, typographic or otherwise? Okay. So if you remember last time, just to summarize where we are in this class, we've basically been introducing like the basic machinery that we're going to use when we start talking about more interesting things. We've talked about these very simple consistency plans, marginal both for means and for quantile. These are just conditions that ask that model are in. But obviously, when they're on their face, they're not getting the wrong average values. So we talk about means and quantiles. We talked about loss functions that are useful in thinking about those quantities. In particular, squared error was useful in reasoning about bias, kind of bias of means, because when we find an incorrect bias, squared error increases, and pinball loss was similarly useful in reasoning about systematic bias with respect to quantiles, because when we find and correct marginal quantile consistency bias, follow up. And then we started last time to introduce some another set of tools that is going to let us talk about how our models perform on a data set with sampled IID from some distribution and transfer our findings from the data set, which is not ultimately what we care about, to the distribution from which the data set was drawn, which is maybe closer to what we know. And so we proved some very simple theorems last time. His main point was making introduce you to a useful tool, the update equality. We proved that if you take some model and you de-bias it with respect to its mean prediction on a data set, then you can be sure, or at least you can be confident to as high a degree of confidence, 1 minus delta, as you would like, that the bias is small, not just on your data set, but on the underlying distribution. Where small means going to 0 at a rate of something like the square root of log 1 over delta, your confidence parameter over n. The more data you have, the more confident you are. And this is basically a direct application of Hupting's inequality, which is going to be a really useful thing for us when we're thinking about means more generally and bounding our out of sample error. And so what I want to start this talk with is, again, proving essentially the equivalent theorem for quantiles. We're going to try to parallel everything we do for means. Quantiles, again, we're going to need to transfer in sample bound to out of sample bound, and we're going to need a slightly different tool for that when talking about quantiles. It's not going to be Hupting's inequality, it's going to be something called the DKW inequality. Before, again, it's one of these basic probabilistic tools that's going to come up again and again and be generally used. Okay. So, good. So, first of all, like, let's think about what Hupting's inequality does and how we estimate like the bias of anything, a model or a point, and why sort of those things match up pretty directly, and why quantiles are different, and why we, when we're sort of trying to debias a model with respect to its quantile estimation, something a little bit different is going on, like why we need to introduce a new tool. Okay, first of all, if I want to know what is the bias of a model on some distribution, it's very much like flipping coins. There's sort of a single quantity that I just average over the example. Like I was estimating the bias of a coin, it would be just, like, is the coin head after a coin flip? Average that over a bunch of sample coin flips. Here it's just, what is the difference between the prediction of the model and the limit? I average that. Okay, so I'm just computing this average. And to debias the model, I just subtract this average off from my model. The only thing I need to do, the only statistical task here, is to estimate the bias of the model. Once I know the bias of the model, I just subtract that off. And computing the bias of the model is just computing an average of this, numeric value quantity. It's exactly like flipping a coin a bunch of times and empirically estimating the bias of that coin. That's why Hupting's inequality is the right thing for us. If you think about how we talked about updating a model, shifting a model to satisfy marginal quantile consistency, it was a little bit different. There wasn't just like this fixed quantity that we would compute delta that we could compute in isolation by averaging something actually off the model. We sort of defined delta through our goal. We're like, all right, let's shift the model by delta, where delta is the shift defined such that after we shift the model, the quantile consistency error is zero, close to zero. But like quantitatively, how would you do that? You'd have to like basically try a bunch of different shifts, right? And estimate the marginal quantile consistency error of each of those shifts, and then use the one that was closest to that led sort of closest to zero bias. Okay, that's the difference. When we're estimating the bias of a model, the mean error, we just compute essentially a single average, and we need to bound how far that average is from zero. How different the empirical average is from expectation. Here, we sort of need to compute like a bunch of different quantile values. And as a function of all of them, if you look at all of them, we see sort of which quantile value is like plus q. As a function of all of them, we sort of pick our favorite. But the difference is that here, we need to correctly estimate a quantile at not just a single point, a quantile not just for a single shift, but we need to sort of uniformly estimate all possible quantiles of the distribution. Any of them could be the shift we want. Okay, so the difference is here when we're sort of trying to think about fixing quantile consistency errors. We need a uniform bound that's going to tell us that simultaneously for every possible shift, quantile consistency error on our data set under that shift is close to what it would be on the underlying distribution. And that's a different kind of bound. That's why we're going to use the tool. Does that make sense? Okay, let me give you a theorem that again is going to be like an extremely direct application of let's say probabilistic inequality, a W inequality. The main expositional point here is let's call it the theorem. Let's set a model S. Any model S. Um, and any data distribution. And again, let's suppose that we've got a data set. C that the endpoint sample IID for our data. Okay, we have the data distribution that's the thing we care about. But the only access we have for the data distribution is that we've got point sample IID increment. We've got n of them. We want to essentially pretend that D is the real distribution. We want to shift our model so that it has no quantile consistency bias on the data set, and we want promises about the underlying. Let delta be the shift. But since we define this new model as that, model F is by delta, but this new model has marginal quantile here. Say on the front. Back to a target quantile. Let's say come up with this shift on the data. These statements are about the empirical distribution on the data set, not the real distribution. And claim it that probability 1 minus delta over the draw data set, or when we're making statements, when we're trying to transfer statements, data sets to distributions, we can never say anything with certainty because we've gotten a really unlucky draw. But with probability 1 minus delta over the draw of the data set, promise that F hat that is marginal here. Alpha, where alpha bound at alpha prime plus square log of delta. So this expression should look familiar to you. This is the same kind of mediation we got when we were talking about the difference between our in-sample and out-of-sample error for marginal mean error with statistical bias. That's not a coincidence. This is sort of the rate to expect for lots of simple estimation problems. But this is going to come out of a different probability. There makes sense. One thing that if you were now Yeah, this is maybe why I wrote, I didn't write that the marginal quantile the error on D is zero because of the discretization, right? It might not be, even if all of the points are distinct, it might not be possible to get zero marginal quantile. Because the error Q is not a multiple of 1 over n. So the discretization. Okay, this is saying whatever it is, it'll be similar in sample and out of sample. Okay, so get it as a good algorithm then might be to get the quantile here as low as you can on the data set, and it won't be much larger. By the way, though, like this kind of discretization error that maybe you're worried about, so even if the underlying distribution is continuous, the discrete distribution will take sort of n distinct values. This will cause you sort of error on the order of 1 over n at most, which is sort of washed out anyway by the statistical error. Like the magnitude of the sampling error is going to be on the order of 1 over root n. So although it's true that the empirical distribution of D is discrete, the quantiles are going to take different values only at the sort of granularity of 1 over n. That's not what you need to worry about. Like that's a lot smaller. Does that make sense? Good. Okay. Application of the DKW inequality. I think that for deeper, I just tell you what that is, and then the proof is going to be just an application of that inequality. DKW inequality in our setting is the following. Suppose we've got any distribution of data points. And can't be just our notation for the label data set. And we've got a data set consisting of n point sample IID. Now there's two objects that I want to compare, and they're the CDF of the real distribution and CDF of the data withdrawn. Then there's the empirical CDF of the empirical distribution. And what the DKW inequality is going to tell us is that as functions, these CDFs are functions. You can sort of plug in any value and get a number out. These functions are sort of uniformly close to one number. They're close not just in one point, but in every point. So, right, so what are the two objects that this thing is speaking of? Well, one is the CDF of the underlying distribution, the NVG. Okay, so let's write that as F of C. Functional. And it tells us, given C, what is the probability? Given an example on the underlying distribution, that the label less than or equal. Okay, so there's going to be some function that, some function that C somehow goes 0 to 1. Right, as the threshold gets higher, it's more and more likely that the label takes some value less than the threshold, and the function is going to specify this whole curve, which is monotone. Starts at 0, goes to 1, but otherwise it looks like anything. We'd love to know this though. If we knew this thing, we could read off all of the quantiles of the distribution. Okay? But we don't have access to this thing. We've got the data set. And so one natural thing we could look at given the data set is the empirical CDF. CDF is the empirical distribution. Okay. So let's data set. It's going to be the PDF of the empirical distribution that's uniform of the data set. And what's this thing? Well, it's just the average over the endpoints in the data set. The indicator that the label for that point less than or equal to our specified threshold. Just the fraction of points in the data set that are below. Right? The true distributional quantity tells us the probability that a newly sampled label will be below C. The empirical CIS that tells us the fraction of points that are below C. Okay, and so this is also like a curve. This curve, as we've already noted, it's going to be like a little bit bumpy. It's not going to be smooth because there's only n points in the data set, right? So there are going to be sort of n points that we have to count. And so, like, what are we going to do to take our model and debias it? Well, we're kind of going to look at quantile prediction made by our model, and we're gonna look at the whole curve, and we're gonna try to pick a shift that causes the quantile to approximate our target. Okay, but we might have to look at the whole curve for that. And so what we want is a theorem that tells us that these two objects are uniformly close to one another, meaning simultaneously for every value of c, the value of these functions is close when evaluated as one. That's the EKW inequality. Okay. What EKW tells us is that deviate here think about if we look at probability that for any value, like largest, the p that induces the largest deviation, and we look at how different the true CDF is from the empirical CDF. Probability that this deviation exceeds c, and it goes 0 and something that looks like e to the minus 2, and so it's telling us, it's to sort of look at the form of this thing. Compared to like the Update inequality, which was bounding a single quantity, basically, like the difference between the empirical average of a bunch of random variables and an expectation. Here, we're sort of uniformly bounding the deviation between every point on these functions. But otherwise, the theorem looks kind of similar, saying that the chance that there is a deviation that exceeds t anywhere goes to 0 at a rate that's sort of like exponential in t squared and n. And so when it's going to start becoming small, it's going to start becoming small when t is bigger than 1 over square root of n. And this makes sense. And this is a useful inequality though. It's sort of telling us that if we have sufficiently many samples, then we can sort of trust the empirical PDF of the sample to be close to the field PDF. These are uniform confidence intervals that we play for empirical. Okay. And so the connection between DKW and our sort of sample complexity theorem is kind of the immediate, but let's go through, let's sort of connect the dots to make sure that it's right. First of all, like, what distribution are we kind of talking about, given this data? Well, the distribution that's going to be convenient for us to talk about, right? Again, we've got, during the distribution that lives in the statement of this theorem, okay, but we actually don't want to talk about the quantile of the label from that distribution. We want to talk about the quantile of the difference between, because ultimately we're interested in how different our predictions are from the relationship between our predictions and labels. So why don't we just define a distribution that's going to capture them? So let's let D prime be the distribution drive our real data distribution by placing label Y for C. It's the residual of our model. But Y minus F. So subtract off the prediction of our model, because ultimately marginal quantile consistency is about the relationship between our predictions and the relationship. Okay, and we'll apply DKW to this. So the premise, right, of the theorem is that delta has been chosen so that this shifted model at hat has marginal quantile consistency error alpha prime. What does that mean? That means that, like, by definition of delta, what we know is that, let's look at an example on the underlying data system. Probability that Y, that most f of x plus delta value the model differs from target quantile Q by alpha. And so, given how we've defined D prime, this is, an equivalent way of writing them. To say that we look at the empirical CDF. D prime evaluated at delta. Label from prime of Y minus F back. Yeah, D prime evaluated at delta. This is within alpha prime. And so, we want to guarantee the full of 1 minus delta. We're looking for a value of T that makes the right-hand side of the inequality here at most delta. We can just apply W with an appropriate choice of T. So, log delta, Y that choice of T, well, And what we learned is that, well, yeah, the thing we knew about the empirical CIS where we particular by triangle inequality. Okay, so if I want to bound the difference between the true CF value of delta and Q, well, we are that up. So most alpha prime plus very far delta. And just expanding out like what this means, what the definition of a CEF is, and what our distribution, how our distribution is defined. Yeah, exactly. Yeah. So yeah, the DKW inequality is basically just a tool that tells us that the quantiles on a sample label distribution are uniformly close to the quantiles on the underlying distribution when the thing we care about is marginal quantile consistency, just a statement about relationships between a certain quantile on the distribution of the residuals of our model, and a sufficient condition is that we have a statement about all points. Does that make sense? Yeah. What oh, this is for all things, but this is a sort of uniform property here, right? So this is why we need something like this rather than just a hunting bound. Like a hunting bound would tell us something about any single value of C. But this is telling us something simultaneously for all. The uniform bound for the whole function. Does that make sense? That's the important thing. That's why this is useful for us in a way that I'm thinking of. Okay, cool. Good. But now, at this point, we've basically developed the basic tools that we need to develop a theory of um, marginal and conditional guarantees of various sorts when we're talking about the underlying distribution. And what I want to spend, the next 25 minutes on is just giving similarly simple examples of what we've done so far in the distributional setting, but in the online adversarial setting. Okay, and already, like what we've been doing in the distributional setting, has been sort of, we've been asking for sort of obviously very weak conditions like bias and only on average. And when you start thinking about the online adversarial setting, I'll remind you what that is, but remind you with words for a second. For the online adversarial setting, there is no distribution. Every day, an adversary, an arbitrary process about which we make no assumptions, will produce a label somehow. Future need not look like the past. And before they do so, we need to make a prediction. Okay, so initially this might seem like a more difficult model than the distributional model, and yes, it will be. But the algorithms we're going to see for guaranteeing sort of marginal guarantees on our prediction are going to be sort of even sillier on their face than the simple algorithms we saw for doing this in the distributional thing. Despite the fact that it doesn't make sense to do something like estimate the mean of the distribution and then predict that, because there's no distribution between the mean. Okay, but like I'm going to show you an algorithm that is like ridiculous, like clearly useless, and yet it satisfies very good marginal guarantee, a very low bias algorithm. And one thing I want you to learn from this is not that this is a great algorithm that you can run and use. This is going to be like clearly a bad algorithm, but that marginal guarantees are extremely weak. Okay, I think of this as part of the motivation for why we want to move beyond this kind of thing. One thing, despite that, maybe just sort of a note on the relationship between the distributional and non-adversarial model is good to understand, and prove some of these points in the notes, but maybe I'll skip over it in class. There is a formal sense in which the online adversarial model is only more difficult than that model. Anything you can do against an adversary, you can also do if there's underlying distribution from which you have samples, and the reverse is not necessarily good. Okay, so let me just define marginal, sort of, what these marginal quantities mean in the online adversarial setting, and I'll tell you, but not prove to you, the sense in which the online adversarial setting is only more difficult than the fact that the connection that holds more generally the other things we do in this class. But I think I'll skip the first. Remember the online adversarial setting for a moment. So in the online adversarial setting, sort of, our algorithm is interacting with the adversary and ground. The adversary essentially takes feature vectors and shows them to us. Then we make a prediction. Then the adversary reveals to us what the label was. Okay, and it goes on, and the interaction accumulates into a transcript, a record of what has happened so far. And ultimately, that transcript is the object range. Whenever we try to prove guarantees about what our algorithm accomplishes, it will be statements about, essentially the transcript, the empirical distribution on the transcript. If there is no distribution, our transcript is the only object we can sort of use to evaluate our prediction. So just to remind you, like, of the definitions of things like marginal mean, and marginal quantile, what does it mean in an online adversarial setting? Here's what they mean. So let's fix transcript 5. Okay, remember, what is this thing? Just a sequence of triple features, prediction, and realization. We'll run the time stack ranging from 1 to capital 10. Here are the predictions for the building. We say that by marginal say error alpha if when I look at the average overall time of the prediction made by the algorithm, this equals the average overall time realized label up to some error. Okay, so it's the statistical bias condition, but there's no distribution now. We're just talking about essentially the empirical distribution of the transcript. It's the after the fact right distribution between prediction and label. We just want that our predictions be statistically unbiased empirically on the transcript after the fact. Similarly, find sort of the online version of marginal quantile consistency. I just look at the empirical frequency over the transcript. That my prediction exceeds the label. Be about so, these are sort of the natural definitions. And again, as I mentioned, there's a formal sense in which solving the online adversarial problem, which means giving an algorithm that promises the transcript will satisfy one of these marginal guarantees after the fact, no matter what the adversary is. It's only a more difficult problem than solving the back estimation problem. And the sense in which that's true is there's a reduction. Okay, there's like a theorem that says, if you have an online algorithm that promises that for any sequence of examples that generates transcripts that satisfy marginal inconsistency, then you can use that algorithm to satisfy these properties on any distribution you want. Okay, and the reduction basically just instantiates the adversary in a particularly non-adversarial way that feeds the algorithm samples from the distribution and then does something with the resulting transcript. Okay. So it's not hard, but the point is just that these aren't two totally unrelated models. Like the online adversarial setting is only harder, and then any problem you can solve in the online adversarial setting, you can also solve in the distributional setting. The reverse is not necessarily true. So we'll see it is true for a lot of problems, which is going to be. But it's not going to be interesting for these problems. These problems are. Okay, so does anyone, look sort of like forewarning that these problems are too easy? Does anyone want to suggest for me an algorithm that will get very good guarantees of marginal mean, no matter what the is? I'm kidding. Well, that's too complicated. Let's pick something more. Wouldn't work, but that would be quite a good idea. But if the example came for distribution everywhere, but otherwise, you get some bounds, but it would be able to say. Yeah, let's predict what happened yesterday. Okay, just to point out, like, this is like not a very useful algorithm, right? What would this mean in the context of like weather forecasting? Suppose what I'm trying to do is to predict the probability it's going to rain tomorrow. Okay. I was sleeping through my classes in meteorology school. So I don't know what to do. And so all I do is if it rained yesterday, I'm going to predict 100% chance of rain today. If it didn't rain yesterday, I'm going to predict a 0% chance of rain. And that's going to be my weather forecast. Yeah, in principle, I get all of this meteorological data. I get parametric, whatever, satellite. I ignore all of that. I don't even know my password to log in to get that stuff. I just predict whatever happened yesterday. Okay, so here's the algorithm. Solid. Online. Marginal. Well, on first day, my strategy is what happened yesterday, but like at some point I was born, I didn't have an observation yesterday, so I just need to predict something. On the first day, I'll probably predict, say a 0% chance of rain. Then what I'm going to do for each day is, like get some features, some meteorological observation, but I will ignore those. And my prediction today, that's the outcome is. And I see what happens today. Useful, but my prediction is going to happen tomorrow. That's the algorithm. And it's like not a very good algorithm, not very useful, but it does satisfy marginal mean differences, giving us any bunch of examples, and actually at extremely good rates, much better rates than I could get if I was trying to do something right at the rates we got in a distributional setting, where at least I was learning the mean of the distribution. I was doing that here. At least I was doing the mean of the distribution. Those were like 1 over root c. 1 over root n. I had an example. Here I'm going to get much better rates. 1 over c. Theorem is that for any one example, sorry, my throat thing. This algorithm online marginal. Read the transcript. That satisfies and the proof. Well, using the fact that our prediction every day is just the outcome yesterday, and our first prediction 0. So when I look at the definition of marginal mean error, right, the difference between average and average. Write that entirely in the function. is just a label. Means that almost every single one of these terms canceled out. But get that. The only terms that don't cancel are my first prediction and my last prediction. First prediction, wow. Okay. And so this is just equal to 1 over t. That's different between, well, my first prediction and the last outcome. My first prediction was 0, and the outcomes are bounded between 0 and 1, and so the most point. So, what it's doing is it's highlighting, the now much more apparent weakness of asking for only marginal appearance. And like you could always do this even without a bound. It's just that, right? Like the labels could be anything. You could always predict what happened yesterday. And you always get this bound at the end. Right? The only place we used that it was bounded was by saying, YT is less than or equal to 1. Right? But you get the same theorem. It's just that it would be the magnitude of the final outcome. That wouldn't be non-trivial in the worst case unless t was bigger than the magnitude of the final. But both in the online and the batch setting, like the magnitude of the numbers you're working with. Right? So like, we had this assumption, we've had this assumption everywhere that the labels are bounded between 0 and 1. There's nothing special about 0 and 1, but more generally, like all of these theorems would have to scale somehow with the scale of the data. Because if I multiply all the numbers you're working with by 1,000,000, your error term is also going to go up by a factor. So that shows up somewhere. Normalizing things between 0 and 1 is another way of like getting rid of that feature. Okay. So good. So where do we go from here? There's a couple of things. So despite the fact that marginal guarantees are sort of very weak on their face, do things like this. People still use them. They are useful in some way. And what we'll see next class is sort of one of those popular uses called the formal prediction. Okay, so at the beginning of next class, I will give you the equivalent algorithm for marginal quantile consistency. And then we'll talk about, this popular area that's called conformal prediction, which is aimed at producing prediction sets that in very general settings are able to promise that marginally at least with any target probability you like, they contain the true label. Well, it turns out that conformal prediction is just an application of marginal quantile consistency. And despite the fact that, we might want stronger guarantees, these things are used. Okay, we'll talk about that. And then after that, we're sort of, you can think of this predictor, this sort of silly algorithm, as pointing you in the direction for what kinds of stronger guarantees you might have. Right? Like, weather predictions like this would be silly on their face, despite the fact that they satisfy terrific marginal. Well, how come? Well, among other things, like quite frequently, I'm predicting like 100% chance of rain, and it doesn't rain. It's not just if it rained yesterday, I'm always going to predict 100% chance of rain. And once it rains every single day, like I'm sometimes going to be wrong. Similarly, quite frequently, I'm going to be predicting a 0% chance of rain, and yet it will rain. And this is like an immediate certificate that I'm not predicting the correct probability. Because the correct probability was 100% chance of right, it was definitely right. But all these 0%. Okay, so like, despite the fact that this is, this predictor gives predictions that are marginally consistent, they are not self-consistent. They are not consistent conditional on the predictions themselves. Right? You can falsify them by looking at the statistical bias of the predictor, not just overall, but conditional on the prediction. The prediction, on the subset of days for which I predict a 100% chance of rain, unless it rains 100% of the time, like I'm going to have significant statistical bias there. Similarly, on the subset of days where I'll predict 0% chance of rain. And so that'll be the first conditional guarantee you start asking. That the model should be conditionally self-consistent. Right? It should have no statistical bias, conditional on its own prediction. That's what's called calibration. Move on.